Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afif bin Muhammad Azani. My matric number is AD110133 and I will represent for our group, which is group 6 from section 10. And I will present for the introduction part and conclusion part. So for the introduction part, which is for background study, is describe the resonance and vibration oscillator. For resonance occurs when the natural frequency of the oscillator coincides with the frequency of the source vibration. For vibration oscillator is a device that is placed at the bottom of small or heavy machineries to reduce vibration created by the machine while it is functioning or in a dynamic state. The existing materials of oscillator in the market is two, which is silicon rubber and subaltern vibration oscillation circular pads. Silicon rubber is non-reactive, stable, and resistant to hard circumstances and temperatures ranging from 55 to 310 degrees Celsius, which is 767 to 472 Fahrenheit, by preserving useful properties. And for subaltern vibration isolation circular pads is flexible anti-vibration pads that can be used as feed, stops, presses, and protectors. Type of vibration isolator, we have three types, which is this one is metal rubber vibration isolator. Metal rubber is a synthetic version of natural rubber. The metal rubber component is formed of metal wire and does not contain natural rubber, yet it has the same flexibility and porosity. For steel spring vibration isolator steel spring isolators can be used on equipment weighing hundreds of tons as well as lightweight precision instruments. And for the rubber vibration isolator the major design characteristic of rubber vibration isolators are used as vibration isolators rubber. For objective of our project the first one is to do research and compare the lowest and highest natural frequency for each form of material. Secondly, finding the best washing machine insulator that can decrease vibration levels while each machine runs at its optimal speed, and to select the best isolated pad material to reduce vibration levels in the stackable washing and drying machine. The scope of the project is all the dimensions and parameters of the isolated pads and optimal fuzzing frequency are given. We developed two designs of vibration isolation used types of vibration isolator with different material and same material. Thirdly, we perform and analyze the lowest and highest natural frequency for each design using matrix iteration method to select the best design. Expected result for our project is to get both a higher and a lower value of highest and lowest natural frequency for the material chosen. The amplitude will increase indefinitely. The reason for this is resonance, which occurs when the forcing frequency equals to the natural frequency. So that's all for introduction part.
Okay, for chapter 2 case study, anti-vibration mats can be made from several different materials. While they are all going to reduce the amount of vibration that transfer to the floor beneath, each material will do so to a different extent. Anti-vibration products for your washer and dryer came in several different forms. While each of these can be very effective in their own right, by nature, some will perform better than others. A few things that we consider are performance, price, material, and thickness. For design 1, mass of the washing machine is equal to 101 kg. Mass of washing machine 2 is equal to 60 kg. Stiffness for isolator 1 is 350 Newton per millimeter. Stiffness for isolator 2 is equal to 550 Newton millimeter. And lastly, the forcing frequency is equal to 52 radian per second. So for design 2, same for the mass for the both washing machine, and the stiffness for isolator 1 is 550 Newton per millimeter, and same as the stiffness for isolator 2. And the forcing frequency is equal to 52 radian per second.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Adri bin Muhammad Saad. My matrix number CD190296. I will explain about chapter 3, Methodology Theoretical. Derivation of equation of motion. To find out which material is suitable as an insulating pad for a washing machine, the highest and lowest natural frequency values were calculated using matrix iteration until the natural frequency value were acceptable or repeated. There are two types of design that need to be considered. Firstly, the design has different stiffness for each insulator, and the second design has the same stiffness. The trial vector we use is general trial vector, which is negative 2.1 and 0.9. Derivation of equation of motion EOM. This is a free body diagram of insulator M2 and M1. Equation of motion F equal to mx. This is for mass 1 and this is for mass 2. In matrix form, N1, 0, 0, M2, x1, x2 plus in the bracket K1 plus K2 minus K2 minus K2 K2 and x1 x2 equal to 0. Details calculation using matrix iteration method of lowest and highest natural frequency on both design. For analysis of first design, as the instruction in the project template, each of the insulator have different value. Mass of washing machine 1 is 101 kilogram. Mass of washing machine 2 equal to 60 kilogram. The stiffness of insulator 1 equal to 350 Newton per meter. The stiffness of insulator 2 is 550 Newton. Based on the information above, we can calculate the natural frequency and the mode shape. Lowest natural frequency and mode shape. What is lowest natural frequency and mode shape? The equation below is obtained by combining the mass and the stiffness coefficient in the equation of motion. As you can see, this is the equation. Matrix K and matrix M was determined by the equation above. Next, we must calculate the inverse of matrix K. K equal to 900, negative 550, negative 550, and 550. For K minus 1 equal to 0.002857, 0.002857, 0.002857, and 0.004675. And M equal to 101, 0, 0, and 60. After inverse matrix is obtained, it can substitute into the standard matrix iteration equation along with matrix and initial trial vector to calculate for x new. This is for x new, K, negative 1, mx. And you will get 0.002857, 0.002857, 0.002857, and 0.008675. 101, 0, 0, and 60. Negative 2.1, 0.9. X nu equal to negative 0.451714 and negative 0.353532. And the eigenvalue and eigenvector can be calculated in the next step as shown in the table below. This is iteration for iteration 1, 2, 3, 4, 5, and 6. Iteration 1, x new is negative 0.451714, negative 0.353532. And largest x new is negative 0.353532 and normalized x new is 1.277717 and 1.000000 and follow with iteration 2, 3, 4, and 5 as you can see in the table. The value for lowest natural frequency and mode shape can be determined by calculating the eigenvalue and eigenvector. As you can see, this is 1 divided by pi, not pi, 1 divided by 0.5 0.07023 times 10 negative 3. And you will get 44.410552 radian per second. The mode shape is x equal to 0.784840 and 1.000000. This is the graph for the mode shape. Okay, the highest natural frequency. The inverse of matrix should be obtained first in order to find the highest natural frequency. As you can see, this m equal to 1, 0, 1, 0, 0, and 60. M negative 1 equal to 0.009901, 0, 0, and 0.016667. Next, we can insert the inverse of matrix that were obtained into the standard matrix iteration equation along with matrix K and the initial trial vector. As you can see, this is x new, the equation that we use. And this is x new 0.009901, 0, 0, and 0.016667. The bracket 600, negative 550, negative 550, 550, and negative 2.1, 0.9. And you will get this answer. The x new in the calculation above will be used in the matrix iteration method to obtain the eigenvalue and the eigenvector for the highest natural frequency. Sorry. This is for iteration 1 until 7. You can see in the table. This is for x new. And this is the largest x new and normalized x new. The highest natural frequency is 16.105192 times 10 3. You will get 126.906233 radian per second. The mode shape of the highest natural frequency is x equal negative 0.756928, 1.000000. This is the graph. Next, analysis of second design. In the first design, both installation of washing machine have different stiffness coefficient, but in the second hand, the isolator have the same stiffness coefficient where it's be 550 Newton meter. However, the mass remains the same as the first design. For the lowest natural frequency and mode shape, the equation below is obtained by combining the mass and stiffness coefficient in the equation of motion. This equation of motion. Matrix K and matrix M was determined by the equation above. Next, we need to calculate the inverse of the matrix K. As you can see, K equal to this number, and you will get this number. After inverse matrix K is obtained, it can be substituted into the standard matrix iteration equation along with matrix M and initial trial vector to calculate x new. As you can see, this is the equation and matrix number for x new. And you will get negative 0.287455 and negative 0.189273. The eigenvalue and eigenvector can be calculated in the next step as shown in the table below. As you can see, the iteration 1 until 6, and this is x new for iteration 1 and 2. This is iteration 3, 4, 5, and 6. And for largest x new and normalized xu, normalized xu you can see in the matrix form for iteration 1 until iteration 6. The value of lowest natural frequency and mode shape can be determined by calculating the eigenvalue and eigenvector. 1 divided by 0.343580 times 10 negative 3, you will get 53.949331 radian per second. And lastly, x is 0.682488, 1.000000, and this is the mode shape for this one. highest natural frequency. To calculate the highest frequency, the same method is used as the first design. The value for the inverse matrix can be directly taken from the calculation in the first design. Since the mass is same for both design, then the value will be substituted into equation. This is a equation that we use, and this is for iteration 1 until 8 for x new, largest x new, and normalized x new. The highest natural frequency is 17.146553 times 3, and you will get 130.944847 radian per second. And this is the mode shape of the highest natural frequency. And this is the graph. Lastly, you can see for isolator design 1 and 2, first natural frequency is 44.411 for isolator design 1 and 53.949 for isolator design 2. And first mode shape x equal to 0.785, 1.000, and for design 2 x equal to 0.683 and 1.000. Second natural frequency for design 1 is 1 to 6.906. For design 2, 130.945. And second mode shape x equal to negative 0.757 and 1.000, and x for second design is negative 0.871 and 1.000. That's all from me. Thank you.
My name is Muhammad Iman bin Alas, and I want to present to you Chapter 4, Methodology of Modern Tool. We are using FreeMat. FreeMat is a free environment for rapid engineering and scientific prototyping and data processing. It is similar to commercial systems such as MATLAB from MathWorks and IDL from Research System, but it is an open source. FreeMat includes several novel features such as a codeless interface to external C, C++, Fortran code, parallel distributed algorithm development, and plotting and visualization capabilities. The calculation that has been done must be validated using a certain method. In this project, for the validation method, we use FreeMat compiler involving the power method to prove the answer obtained. So for design 1, this is the validation answer for the lowest natural frequency. So we got the answer is 0.7848. Next is the validation answer for highest natural frequency, that is negative 0.7569. Next, for design 2, the validation answer for the lowest natural frequency, we get 0.6824, and validation answer for the highest natural frequency is negative 0.8705.
So I will explain a little bit about chapter 5, which is result and discussion. And for 5.1, matrix iteration method. And this is the table of the first natural frequency and the second natural frequency by using matrix iteration. And for design 1, the value at first natural frequency and second natural frequency is 44.410552 radian per second and 126.906233 radian per second respectively. And it is obtained from two different materials in which stiffness coefficient K1 and K2 is 350 Newton per millimeter and 550 Newton per millimeter respectively. As for design 2, the value for first natural frequency and second natural frequency is 53.949331 radian per second and 130.84487 radian per second respectively. And the stiffness of coefficient for K1 and K2 is the same because it used the same material, which is 550 Newton per millimeter. And this is 5.2, the validation using theoretical result, and we are using FreeMat. And this is the tabulated data that we got. And this is the screenshot from the free mat app for first natural frequency and the second natural frequency for isolated design 1. And this is for isolated design 2 for in which this is the first natural frequency and this is the right one is the second natural frequency.
Question part is, our calculations show that we have achieved our goal of identifying the lowest and highest natural frequencies for the first and second design of isolator 1 and isolator 2. The conventional matrix iteration yielded the lowest natural frequency of 44.41 radians per second and the highest natural frequency of 136.9 radians per second for the first design isolator 1. For the lowest natural frequency of isolator 2 is 53.95 radians per second and the highest natural frequency is 180.84 radians per second. Isolator 2 has a higher value than isolator 1 at both frequencies. Then we obtain the mode shape for both materials using the conventional matrix iteration process and validated it using the eigenvalue and eigenvector calculators. Isolator 2 is the ideal dampening material to utilize because it has a greater and lower natural frequencies than isolator 1. So that's all from our group. 6. Thank you.